So now it's time for the Sobel operator, which calculates a sort of fuzzy gradient and then measures the length of the gradient vector for each pixel. So we can see the gradient calculated by turning this off, and we'll see that there is some red and greenness in here, and that is because red means a large amount of change in the U direction or the X direction, and green means a large amount of change in the V or Y direction. It looks a lot like a normal map, except there's no blue in it, but it's not quite a normal map yet. We can turn it into a normal map, but that is for the next tutorial over there. The gradient can also be described as the direction of steepest descent, which means that if you took a height map and put in here and took the gradient of this height map, then the gradient would basically be a vector field where each vector would denote the direction a ball would be most likely to roll if you just put it on the surface right there and just let go. So that is what is meant by steepest descent. The reason why I was calling it a fuzzy gradient is because we sort of don't take the real gradient, we take a sort of expanded gradient that includes the diagonals. So here we have the red kernel and the green kernel, and you can see that I am having values both for on each side of the middle, but also in the diagonals. And the reason why this is done is because Sobel is intended as an edge detection algorithm, and so to get a continuous edge even when the difference is relatively small, it's just better to give it a little bit of fuzz in there. We can get a more quote-unquote true gradient by bumping these numbers down to just being on the sides and not in the diagonals. And if we do this, it doesn't immediately look very different. It just loses a little bit of the intensity. However, this version of it is one we're going to see a whole lot more of later on. So the way we are doing this is really just applying two different kernels to each of the two channels. So it's really just in one pass, because you don't have to sample twice in order to do this. So if we open up the material function, you will see that we're still sampling the same number of times. We're just piping it into two different kernels. There's a kernel 2 down here and a kernel 1 up here. So just a whole lot of multiplies to get all those vectors that we pipe in and turn into a kernel from up here and down below. You could think of it as a multipass function, except it's not as performant that way. And you could think of it as first you do a convolution for the red channel, a convolution for the green channel, and then a final convolution for using the red and green channel to get the length of the vector that they generate together. So in that way, we will have some examples where we will iterate between some buffers, and then at the end we will perform another operation to finish it off.